Have a look at this molecule. You might already recognize that it can exist as both E and Z isomers. But here's the question. Is this particular arrangement the E isomer or the Z isomer? Well, this is exactly what we're going to be looking at in this video as we explore what the Cahn-Ingold-Prelog priority rules are and how we can use them to assign priority groups to help identify E and Z isomers of alkenes. But first, let's just remind ourselves of what geometric or EZ isomerism is. Geometric or EZ isomerism is one of the two types of stereoisomerism you'll study in A-Level Chemistry. Stereoisomers have exactly the same molecular and structural formula, but differ in how their atoms are arranged in 3D space. In EZ isomerism, this happens because of the restricted rotation about the carbon-carbon double bond in alkenes. However, not every alkene shows EZ isomerism. In order for it to occur, each carbon atom in the carbon-carbon double bond must be attached to two different groups. When we look at simple alkenes like butene, deciding whether the molecule is an E or a Z isomer is relatively straightforward, as it's obvious which atoms or groups of atoms we're comparing. No disrespect to hydrogen, but it's never going to be considered a priority. If the priority groups are on opposite sides of the double bond, the molecule is the E isomer, and if they're on the same side, then it's the Z isomer. But as soon as we start looking at more complicated molecules, things start to become much less obvious. If a carbon atom has two different atoms or groups of atoms attached to it, how do we decide which takes priority when we're considering whether it's above or below the double bond? Well, that's where the work of three brilliant scientists, Cahn, Ingold and Prelog, comes into play. The Cahn-Ingold-Prelog or CIP Priority Rules help us to assign priority to groups attached to the carbon-carbon double bond. This is done by comparing the atomic number of different atoms in the groups. And this introduces our first ridiculously common mistake. For some reason, students are obsessed with wanting to compare relative atomic mass numbers, and that's completely the wrong thing to do. It's the atomic numbers that we compare. So let's have a look at these rules in more detail. When determining priority, we start by looking at the atoms directly bonded to a carbon atom in the carbon-carbon double bond. The group containing the atom with the higher atomic number is given priority. But if the atoms directly bonded to each carbon atom are the same, we then compare the atoms directly bonded to those atoms. If we find a difference, the group containing the atom with the higher atomic number has priority. And if those atoms are also the same, we continue comparing equivalent atoms further into the groups until we find the first difference. When we find a difference, the group containing the atom with the higher atomic number has priority. Once we've identified the priority group on one carbon atom, we repeat the same process for the other carbon atom in the double bond. We can then finally compare the positions of our two priority groups. If they're on opposite sides of the double bond, then it must be the E isomer. And if they're both on the same side, so either both above or below the double bond, then it's the Z isomer. Now at this point, I fully appreciate there are lots of ifs and thens in that set of rules. And if this is your first time coming across these rules, you're probably wondering what the heck is he talking about. So to help us fully understand these rules, let's apply them to a few worked examples to see them in action. Okay, so let's start with something relatively straightforward. Here we have 2-chlorobutene, but the question is, do we have E2-chlorobutene or Z2-chlorobutene? Well, let's apply our rules to find out. So let's start with the carbon atom on the left-hand side of our carbon-carbon double bond. Now, some of you might immediately recognize that the methyl group is going to take priority in this case. But let's work through the rules to get us into a consistent habit. Sticking to set routines and procedures will mean that we're always going to be able to answer exam questions, even the horrible and confusing looking ones. So we compare the atoms directly attached to the left-hand carbon. We have a hydrogen atom or a carbon atom. They're different, so we can immediately compare their atomic numbers. And I'd always suggest using your periodic table just to make sure you don't make a mistake in the heat of the moment. Hydrogen has an atomic number of 1, whereas carbon has an atomic number of 6. Carbon has the higher atomic number out of the two, and so the methyl group becomes our priority group for this side of our carbon-carbon double bond. Now let's have a look at the right-hand side of our double bond. The carbon is directly bonded to a chlorine atom and a carbon atom. Again, they're different, so we can immediately compare their atomic numbers. Chlorine has an atomic number of 17 and carbon has an atomic number of 6. Chlorine has the higher atomic number, and so the chlorine atom becomes the priority group. Now we can compare the positions of our two priority groups. In this particular arrangement, we have one above the double bond and one below the double bond. So they're on opposite sides of the double bond, which means we have an E isomer. So it's E2-chloro-bute-2-ene. Now let's move on to a slightly more complicated example, one where we don't immediately have two different atoms bonded to the carbon atoms within our double bond. So here we have 1 bromo, 1 chloro, 2 methyl bute-1-ene. But again, the question we need to answer is whether this is the E isomer or the Z isomer. Let's take a look. So let's start with the atoms directly attached to the carbon on the left-hand side of our double bond. Remember, we're trying to build a repeatable process that we can follow each and every time. The left-hand carbon is directly bonded to two carbon atoms. There's no difference, so now we have to take a look at the atoms bonded directly to those two carbons. The top carbon is bonded to 3 hydrogen atoms, whereas the bottom carbon is attached to 2 hydrogen atoms and a carbon atom. We now have our difference. Out of those atoms, it is carbon that has the higher atomic number. Hydrogen's atomic number is 1, whilst carbon's is 6. That means the group that contains this carbon atom, the ethyl group on the bottom of the molecule, becomes our priority group. Because at the point we had our first difference in atoms, it was that group that contained the atom with the higher atomic number. Some students want to say that it's the priority group because it's the longer carbon chain. And whilst yes, it does have the longer chain, that isn't why it's the priority group. It all comes down to which group at the first point of difference contains the atom with the higher atomic number. Okay, so that's the left-hand side done. But what about the right-hand side? We look at the atoms directly bonded to the carbon of the carbon-carbon double bond, and we have a chlorine atom and a bromine atom. They're different atoms, so we can compare their atomic numbers. Chlorine has an atomic number of 17, whilst bromine has an atomic number of 35. Bromine has the higher atomic number, and so becomes the priority group. Now we can compare the positions of our two priority groups. They're both below the carbon-carbon double bond, and so are located on the same side of the bond, which means that this is the Z isomer. And so we have Z, 1 bromo, 1 chloro, 2 methyl bute-1-ene. Now let's take a look at our third and final example, one that reiterates that the chain length of the groups has nothing to do with determining the priority group. Now this substance contains an ether functional group, which you're not expected to be able to name. So we're just going to focus on identifying whether it's the E or Z isomer rather than trying to give it its full IUPAC name. Once again, let's start with the carbon atom on the left of our carbon-carbon double bond and look at what is bonded directly to it. In this case, it's bonded to 2 carbon atoms. Following our rules, we now need to look at what each of those carbon atoms are bonded to. The top carbon is bonded to 2 hydrogen atoms and an oxygen atom, as is the bottom carbon. So as there's no difference, we need to move on. Now there's no point looking at what's connected to the hydrogen atoms, as hydrogen atoms only make one bond, so there aren't any further atoms to compare. Instead, we look at what each oxygen atom is bonded to. In the top group, it's bonded to a carbon atom, and in the bottom group, it's also bonded to a carbon atom. Still no difference. So we continue by comparing what each of those carbon atoms are bonded to. The carbon in the top group is bonded to 3 hydrogen atoms, whilst the carbon in the bottom group is bonded to 2 hydrogen atoms and a bromine atom. So we now have our difference. Bromine's atomic number is 35 compared to an atomic number of 1 for hydrogen. As bromine has the larger atomic number, the group containing bromine becomes our priority group on this side of the double bond. But notice something interesting. The length of both of these groups is the same. Determining priority has nothing to do with the length of the chain. Now moving on to our right-hand side, we compare the atoms directly bonded to the carbon atom in our double bond, and we again have two carbon atoms. So we compare what each of those are directly bonded to. The carbon in the top group is bonded to two hydrogens and a nitrogen atom, whereas the carbon atom in the bottom group is bonded to two hydrogen atoms and an oxygen. We now have our difference, so we compare the atomic numbers for oxygen and nitrogen. It's close, but oxygen pips it with its atomic number of 8 compared to nitrogen's atomic number of 7. Therefore, the group containing the oxygen atom becomes our priority group for this side of the molecule. And again, if you look closely, both of these groups have the same length of chain too. Finally, we compare the position of our two priority groups, and they're both on the same side. They're both below the carbon-carbon double bond, and so we have the Z isomer. So whenever you're determining whether a geometric isomer is an E or a Z isomer, remember to follow the same process every time. First, assign priority to one of the two groups attached to the first carbon of the carbon-carbon double bond. To do this, compare the atoms directly bonded to that carbon atom. If they are different, the group containing the atom with the higher atomic number has priority. If the atoms are the same, compare equivalent atoms further into the groups until you reach the first point of difference. The group containing the atom with the higher atomic number at that point has priority. Repeat this process for the other carbon atom in the double bond. And once you've identified the priority groups, compare their positions. If they're on the same side of the double bond, the molecule is the Z isomer. If they're on opposite sides, the molecule is the E isomer. And that's how the CIP Priority Rules provide a consistent method that chemists use every time they identify E and Z isomers, regardless of how simple or complicated the molecule might look. And this is the final video in the Introduction to Organic Chemistry topic, and the playlist containing all of the videos for this topic is on your screen now. In the next video, we'll begin looking at the chemistry of alkanes, starting with their structure, naming, and physical properties. And for ongoing support with A-Level Chemistry, please feel free to subscribe to the channel.